formula, but again, it's exponentially decaying with the number. And then the expected value, if we just think we're probably going to have a lot of photons, and this is kind of like a semi-classical argument where we're not super quantizing the whole system, we're just saying we're at a high temperature, we're going to have a bunch of photons flying about, so we'll just use the expectation value as the actual number of photons. We won't handle this any more probabilistically than that, and the expectation value turns out to be this. And for anybody that's studied quantum mechanics before, you'll recognize this. It actually holds for any particle that obeys Bose-Einstein statistics. So once we have those two, the density of states and the occupancy for each state, then we can multiply those together to get the distribution of the frequencies. So how much energy would we be expecting to measure at each frequency? We just multiply those two expressions together, and we get this result. So this was actually a great triumph for Max Planck, who was the first one to write down this formula. Now, he didn't have the benefit, he wrote this down in 1900, and he didn't have the benefit of well-defined quantum mechanics having proven out to be really useful. So this was actually, historically, it kind of went in the reverse. They had what was later by Paul Ehrenfest called something called the ultraviolet catastrophe, which is that if you tried from first principles to predict how much energy you should get at each wavelength, you would get this black line. And the black line, I should really flip this around because this is wavelength. So this is low energy and this is high energy. And so the black line says this should go up as the fourth power of the temperature the fourth power of the frequency, and there it goes up, and it should just, the entire universe should explode as soon as anything goes above zero temperature. So clearly that was wrong. And what Planck did was, instead of sitting down and saying, there needs to be quantum mechanics, he looked at the experimental curves, and he said, let me see if I can fit these. And what he wrote down that fit them best was this. And it was only like 5 years later that Einstein came in and said, well, let's think of this as if, and at the time, of course, there was no word photon, there was just electromagnetic waves. Everybody agreed that they'd be waves, and so Einstein came in with this crazy idea that, the statistics here that make it look like, from this formula, which apparently works and matches experiment, the statistics look like you've got these particles of light, and you have integer numbers of particles of light, and that was actually the starting point for the development of quantum mechanics. And so I've actually come at that in the backwards direction from the way it was historically developed, but it's easier to do that from now we know how quantum mechanics works and get the answer than to go the other way around. Okay. So if we need to run, thank you so much for your time. If you can stick around for a couple minutes, I'll give you a little bit more idea of some of the more interesting topics.
Full, so I can go now.
Yeah, no problem. Thanks for coming. So, we talked about the math. We've gone through quantum mechanics. And by the way, this whole idea of momentum being a superposition of position eigenstates, and the position operator then is also a superposition of the momentum eigenstates, means that you can't have a particle, or you can't have any system that's simultaneously in a position eigenstate and a momentum eigenstate, because the two are superpositions of each other. It's not the same basis. It's just like if you have x, y, z along the wall directions of the room, and I have x, y, z along the diagonals, we can't agree on one vector that's an eigenvector for both of us. Or I should say a basis vector for both of us. So that is the fundamental concept underlying what's called Heisenberg's uncertainty principle. So have you ever heard of the uncertainty principle? There's that for position and momentum, and it turns out there's that also for energy and time. So what that means is that you can actually violate energy conservation as long as you only do it for a short time. And the more you want to violate energy conservation, the shorter amount of time you're allowed to do it for.
Yes. So I read something about this engine that can generate thrust without any fuel. It's called, I don't know, it's
Yeah, it's like the M device or something. It's a
M-Drive?
tapered, yeah, M drive. Yeah, it's a
Yeah,
tapered
yeah.
copper. So people are thinking that that has something to do maybe with what's called 0-point energy.
yeah.
And so what it turns out for some of these systems, the electromagnetic field being one, the lowest value, the lowest energy eigenvalue is still higher than 0. So it's a little bit weird because you can only take a system into these states that have the right eigenvalue, but you'll never measure the electric field energy to be exactly 0. It'll always be greater than 0. Now you can't do any work with it, so that's what makes me skeptical that the M drive is powered by 0-point energy. You can't do any work with it, but you'll never measure exactly 0 energy with these systems because the lowest energy eigenvalue is greater than 0. So that's a little bit weird. So black body radiation is one example of a system that you might study in atomic physics, which in physics departments is now more often called atomic, molecular, and optical physics. If you wanted to study this, you would encounter the principles of operations of things like lasers or your MRI. The MRI uses the magnetic moment of the nucleus, and so when it was developed, it was called nuclear magnetic resonance. But people stopped using that term because everybody was scared to go to the hospital and have something nuclear done to them, even though it had nothing to do with fission or fusion or any nuclear bombs. So they had to, oh, it's magnetic resonance imaging. Yeah. So there's that. Interferometry is a really interesting topic, which is you can take an electron, you can send it through a maze where it only has 2 possible places to go. It can either go this way or it can go this way. And it will somehow choose both at the same time. So interferometry is really interesting. You can do that with neutrons. I think people have even done it with molecules, if I remember correctly. And this is actually a possible interferometry energy level diagram for some atoms. Bose-Einstein condensation is also a trendy topic. So basically that's cooling a bunch of atoms or another system to where all of the particles in the system are in the same ground state or in the same energy state. That doesn't usually happen, but if you cool it down enough, it will, and then there's some weird properties there. Quantum computing, I kind of separate that from quantum algorithms, but this is actually, quantum computing is building a system that will do quantum algorithm computations utilizing quantum mechanics. And then quantum teleportation, I hate that phrase because it's super trendy as a phrase. It's not the transporter from Star Trek. It's just, you have a particle over here, let's say you take a photon over here, you know the polarization here, you put it through an apparatus that destroys the polarization over here, but it's connected to another apparatus over here where the polarization that you had over here gets reproduced over here. And if you're going to look at atomic physics, then learning spherical harmonics would be very helpful. Condensed matter physics is actually, oh, and I wish I had good atomic physics references, but the one atomic physics class I took, it was all the professor's notes, and I'm not even sure I have them anymore, so I don't know any good atomic physics textbooks. Condensed matter physics is actually what I studied. It's the physics of materials. You can look at things like magnetic materials. You can learn how transistors work, like those that are in your phone or in your computer, in the whole semiconductor sphere. That's actually what this is. This is, if you're in a semiconductor crystal, if you're in a silicon crystal, then these are all of the energy eigenvalues depending on the direction that you're facing in the crystal. So this axis down here is the direction you're facing in the crystal. And there's an area in here where there are no energy eigenvalues, and that's called the band gap.
Have you heard of graphene?
Sure.
Yeah, I just was watching, we were watching a thing about it the other day, and it's new super metal.
Yeah, and it's a really interesting system because condensed matter physicists for years and years have had these 3-dimensional systems, which some of them you can model and some of them are too hard. And so a lot of times to simplify the problem, what they'll do is they'll take it and they'll say, well, if this material existed in only 2 dimensions, then we could have the math be so much simpler and we could predict a lot of its properties. And so it's neat to see graphene be this almost 2-dimensional system, which you can model mathematically very easily.
because when, what is it, the new nucleus comes about, it just tries to find the next open spot. And so, or I might be getting the nucleus and.
So graphene's, as I understand it, graphene's interesting properties are for the electrons. So the nuclei are very heavy, and the electrons are swimming in this sea of nuclei, and it's the electrical
And
properties.
they're only attracted to the negative and positive.
The voids.
And then it creates a perfect hexagon.
Mm-hmm.
So that's what makes it so strong.
If you're gonna go into, and superconductivity has been studied for about 100 years, in that's matter physics too, and it's still a hot area of research. If you're gonna go into solid state physics as an area that you want to learn more about, here's 2 books. There's this one, and where's my other one?
We have Ashcroft and Merton.
No, I don't recommend
You don't
Ashcroft.
like Ashcroft?
No, it's still completely esoteric to me. So there's the other one.
I saw this video on YouTube from, like, I think it was some kind of, like, from 40s or 50s, it's old video. A video of, from some professor from Atlanta that was showing the properties of liquid helium. So you put like
Yes.
condensed liquid helium and then go below critical temperature.
And it becomes a superfluid.
Superfluid.
Yes. And it's just
lines
like
on the walls and.
just like a superconductor has no electrical resistance.
Without any.
Yep. Just like a superconductor has no electrical resistance, a superfluid is a liquid that has no viscosity. So it moves without friction.
It just comes out of, pours out of a, sieve or bottom of the glass without any. It's just amazing.
Yeah, it's really bizarre.
Really
It just moves around without any.
So if you give it a push, and if you have a layer of it on top of itself,
Yeah.
you give this layer a push, and just like if you put a current in, and the current will go forever in a superconductor, this thing will slide along itself forever.
Yeah. You pour it in a filter, it'll just.
It starts to pour over the edges.
Over the edges.
As the surface tension pulls it out, and there's no resistance to that.
Yeah. So it just empties itself.
So the next area, which is a little bit more advanced, is quantum field theory. I don't have a lot of experience with it. I've done just a very little bit of studying it. This would be useful if you want to know anything about particle physics, the Standard Model, stuff they do at CERN, at the LHC, or also if you're interested in getting into string theory and understanding that's built on quantum field theory. Basically, the idea is that every point in space has a quantum field associated with it. So you don't have an electron that kind of zips from here to there. You have something called the electron field, which is everywhere. And what we see as electrons are excitations of that field, just the same way as you have an electromagnetic field that has excitations as photons. It would be good to start with some classical mechanics, Lagrangian mechanics, to get the math there, which is much simpler, and learn something about perturbation theory and quantum theory. If you want a good starter book for quantum field theory, I recommend this one.
In a nutshell. That's so
That's what I like about this book it's this super esoteric subject, but the guy actually is like pretty comedic throughout it. It's pretty silly, yeah.
I think he has a book on gravitation in a nutshell, like general relativity.
GR in a nutshell too? Oh, I didn't know that. Yeah. We also have, there's been a lot of research since the 1990s in algorithms that can be done faster by a quantum system than by a classical system. So I call this quantum algorithms. One of those is factoring large prime numbers, which if you know anything about encryption, it would be useful to be able to factor large prime numbers quickly. Another one is to search through a space and find something. I don't know if search will ever take off on the internet, but maybe it will, and if you had a faster search algorithm, I'm joking. Maybe it will. Maybe, if you had a faster search algorithm, you could make some money. Superdense coding, you can actually put more information into a quantum system, double the information into a quantum system than you can in an equivalent classical system. And then finding ways, there's a lot of error correction methods, especially with transmitting data, and that becomes more difficult with quantum systems, so there's a lot of work on that. You may already know these if you're into computer science at all, big O notation and P versus NP, that's useful for learning about how quantum algorithms can be advantageous. This is a book on that subject. It's more for a popular audience, but it does have a little bit of math in it. So it's actually a nice overlap between the non-technical and technical worlds.
Yeah.
And last one is my favorite area, which is what's called foundations, to make it sound more legitimate. It used to be called philosophy of quantum mechanics or philosophy of physics. And so it's, it can be mathematical, but it doesn't have to be. There's a number of interpretations for what does it mean to have a wave function collapse. Does the wave function actually collapse, or is there some pilot wave that collapses and the actual electron is a dot that rides this pilot wave? Is it the fact that the possible outcomes actually all occur and they're just occurring in different universes that split off from one another? Is it possible that any wave function collapse is just due to the fact that the system becomes decoherent, that the quantumness of it kind of degrades over time because of interactions with the measurement device? So all those kind of interpretations. Is there not such a thing as reality before a measurement? You know, that's another interpretation. So all those interpretations are debated hotly. The measurement problem is this whole, how come it has to go into another eigenstate when you measure it? How does that happen? Does that happen discontinuously? What makes a measurement? What causes, how do we distinguish a measurement from a non-measurement? And then entanglement is a really interesting concept where you take two electrons or two photons or more particles that are in a joint state. So they're in a single quantum state. You can separate them, and when you measure this one, you're also simultaneously measuring this one. And so you can collapse this one's wave function from over here instantaneously, and then measure it over there, and you'll find that you get a complete correlation. So if this photon is horizontally polarized, when you measure it over here, you know that the person over here would measure it with vertical polarization if they were measuring the same directions as you were. So there's a lot of interesting philosophy there about how reality can't quite correspond to the cause and effect type relationships that we kind of have everyday intuition about. And if you're interested in that topic, this is a really good starter book. It's pretty old, but it's really, really good, really well written. This is a book for popular consumption that you may have seen in bookstores, and this is a book where they interview a bunch of different specialists in quantum physics, atomic physics, philosophy, and this is pretty recent. This is maybe 5 years old, and it's a really good way to see all the different viewpoints within the field. So, if you want to play with the polariscope, you're welcome to do that. Otherwise, I'm happy to answer any questions, and thank you all very much for coming.
Thank you.
Thank you for the time.
Did I give you that book back, or do you have 2 copies?
You gave me that back.
Okay.
So you said Eigen means something in German.
What's that?
Eigen.
Eigen, yeah, it means own or self. Like this is my own arm. Mine Eigen, I forget what it is. My own head, mine Eigen Kopf.
So in CERN, when they're trying to find these new particles, what is the importance of?
So what they've done is they've written out basically what amounts to a Hamiltonian, although they put it in a little different form that they call Lagrangian. For it's easier to use this Lagrangian, which is in classical physics is the kinetic energy minus the potential energy. And so their Lagrangian includes interactions for electromagnetism, strong force, and weak force. And when they solve those different equations, what they find is that at higher energies, you should be able to produce thus and such excitations in the different fields. And when they predict an excitation that they haven't experimentally confirmed, that's when they're looking for a new particle. And these excitations that are hard to find usually decay very quickly. And so what you're looking at is an excitation that then branches off into a bunch of different excitations, which then branch off into their own subparticles. So you got a particle that decays into other particles that decays into other particles. And so when they do a collision, they look at the decay remnants, or the decay products. And some of them, like neutrinos, are impossible to measure, so they infer the loss of energy as something went out that I didn't know what it was, and I couldn't measure it. And they try to figure out, based on how often they see different types of decay products, what caused that, what particle existed immediately after the collision. And there's usually a bunch of different candidates, so what they end up doing is they just do statistically, okay, well, I'm going to botch this because I'm not a particle physicist, but like if we're looking for the Higgs, then 1/8 of the time it's going to decay into 2 protons, and those are going to look also like a decay as if it was a Z plus and a Z minus particle, and so 99% of those decays are going to be Z plus and Z minus, so we have to know how often those are going to be, and then 1% of those decays could be one of these modes for Higgs decay, and then what are our other modes for Higgs decay, and what's gonna muddle up the noise, the signal that we want to get for that from other decays. And so what they basically do is they say, we've eliminated these as possible causes for this excitation, and we've taken out most of the events that we've seen, but there's a little bump of events at this energy, and therefore we think there's an excitation at that energy, and that excitation is consistent with this type of particle with this spin or whatever. So that's what they do. One of the other things that they would like to try to see is, now they're getting up to high enough energy where maybe they can make a microscopic black hole. And they will see the evaporation products of that. Well, a microscopic black hole.
Jump in it?
That's a different meetup group. They're down the hall. So they don't have any evidence for those yet, but it would be really interesting to see if they could make. It would be a major coup if they could actually produce them and verify that they were producing them. And so there was this really prolific time in the 60s and 70s and early 80s where they were figuring out the strong force and the weak force, and they were like, oh, there should be this particle and this particle, sometimes called the particle zoo, which are just all these compositions of quarks usually, and we should have these 3 quarks together, or we should have these 2 quarks together, and we should be able to see this and that. And so they were building these accelerators, and like every week they would announce a new particle, and it would be some predicted particle, and it would be just some triumph, and they just expected that would go on forever, but eventually they ran out of particles to find and so like the late 80s on, it's been, you had the top quark in the 90s, and you had a few things here and there that are very esoteric, and the Higgs boson in 14? Anybody remember? Higgs. When did they confirm the Higgs? Was that 2013? Yeah. And what it's going to be from then out? Well, maybe there's 5 Higgs instead of 1. So that's so they're going to keep trying to find stuff, or maybe we'll find a supersymmetric particle, or maybe we'll find dark matter. Oh, not a fan of supersymmetry. Wow. I thought it was. I was never a fan of it either, but I just thought it was accepted wisdom. Oh, good.
No,
Good.
it's you're either particle or you're symmetry.
Gotcha.
Both will each do your head in, but with supersymmetry, it doesn't explain where you get something out of nothing, so the Big Bang cannot happen. And with particle, it can say that the singularity caused by, let's say, something that's, powerful, I mean, like unimaginably powerful, like a black hole,
Mhm.
actually lead to multiverses.
So you like the multiverse explanation?
I do. I think
Okay.
that, and that everything now, and from like the moment the Big Bang was to the end of time, to the end of the universe, 14 trillion years from now, has all existed, and everything that will be has ever been, and
Block
it's all-
universe.
Yeah, it's
Yeah.
all been done.
So that's kind of the debate is quantum mechanics deterministic or is it probabilistic? If it's deterministic, then everybody in the 18th century will be very happy. Whoops.
By deterministic, you mean chaotic or?
No, by deterministic, I mean
No free will.
Schrodinger's equation tells us if we know the state, then we know how it will evolve. And the measurement postulate tells us that if we know the state, then as long as it's an eigenstate, then we know what the measurement will be. But the Born rule says that if it's a superposition of eigenstates, then we can't have a deterministic theory. Which then philosophers then say, well, how do we have a deterministic theory at the everyday scale of things that works really well in Newton's laws? That's built on a probabilistic theory. Is that sensible? So then some philosophers will try to argue that quantum mechanics can't be complete that way. But for that, I would say you could argue that if any time you have a system of large numbers, then it's going to collapse into something that's very, even if it's probabilistic within a very narrow region. Like how many coin flips do you need to know that you're going to get a half the time heads and half the time tails? You know, if you do it 100,000 times, you probably know you're going to get pretty close to half. So. Anyway, feel free to play with the polariscope, check out the books. Other questions?
Can you zoom in on the bit about superposition?
Yeah.
Well, sorry, there was some down a bit where we had to sum the law. Up at the top. Yeah.
Oh, no.
So that CQ in your Born rule, is that CQ, that coefficient?
Yes.
So where does the eigenvalue come into your superposition definition here?
So the easiest one is if it's eigenstates. So then the eigenvalue, well, actually in this equation, it just shows up, it pops up, it's a separate equation, right? So you've got this, and if I have Q, then I'm going to get a measurement that gives me the eigenvalue Q. So once I operate on this, then I'm going to get one of the eigenvalues. So I operate on this entire sum, and my measurement is going to give me one of the eigenvalues. But the eigenvalues are kind of not,
They're not in there.
they're not showing up here, but when you decide what operator you want to use, then you know the possible eigenvalues.
But so and CQ is the probability that you get that eigenvalue.
Well, here's the weird thing. It's the magnitude of CQ squared. So the wave function, this CQ, is the square root of probability.
Okay, fair enough.
What does that mean?
So,
I have no idea.
But is
Square root of
that a
probability.
property of an eigenvalue, that the sum of the square of the coefficients is going to be 1, or is that
We
a
require
definition?
that.
It's
We
required.
require that so that we can get probabilities that make sense. They're real numbers between 0 and 1.
So it's part of how you pick what your eigenvalues
So we require that if we're going to describe quantum mechanics as this set of operations on state vectors, then we require that any state vector have a magnitude of 1 in order that Born's rule give us a probability between 0 and 1 that's a real number.
Did people try to make things be state vectors and then they're not? Like it doesn't work, it doesn't fit that rule?
I mean, I guess you could try, but I don't have a good example of because none of the textbooks are going to have that.
I don't have a good feeling for how much of this is physics and how much of this is
Math.
people defining a system.
Yeah, so you can look at it as I've defined this whole, or physicists have defined this whole scheme, and they've put in these assumptions. The assumption is states correspond to vectors, measurements correspond to eigenvalues, the vectors have to be normalized, so they have to have a magnitude of 1, and a measurement of a superposition will put the system into the eigenvalue that's measured, and the probabilities will be the coefficient squared. So you take those set of axioms, And you can say, here are all the conclusions that I can derive from those axioms, and guess what? They all work, the conclusions all match experiments. And actually even now, like in mathematical physics or in philosophy of physics, you can probably still get a PhD if you can write down a novel set of axioms that end up leading to the conclusions of quantum mechanics.
What about the state vector? What about the dimensions involved in the basis? You said can position momentum, so it can't be a combination.
Yeah,
Dimensions
so,
wise, how does it work?
so this is where it gets a little bit tricky because these vectors really have kind of all of these properties at once. You can take a system and you can measure position in it, you can measure angular momentum, you can measure energy, and those may not be compatible observables, which means you may not be able to know that the system is an eigenstate of all three at once. But it's a little bit like, let's think about position, and let's actually turn position, I hate to do this, let's turn position into a vector. So that there's actually three states. We put it into three states. We have an X state, we have a Y state, and we have a Z state. And so we have an X measurer, so we have an X operator, we have a Y operator, and we have a Z operator. The Z operator won't tell us anything about X, but it will tell us where we are in Z. So Z, X, and Y are all compatible observables. So you still have these infinite eigenbases, an infinite Hilbert space for Z, an infinite Hilbert space for X, and an infinite Hilbert space for Y. But we can say that when we measure X, we're not really disturbing or doing anything with Y and Z, so we can kind of ignore it. And we can also measure X and Y to infinite precision at the same time if we want to, because they're not superpositions of one another, they're independent. So in a lot of ways, like I didn't even talk about the fact that this electron has an intrinsic angular momentum, which is called a spin. And so if we're measuring the position of the electron, we're usually not thinking that we're affecting the spin, or if we do, then we account for it with the spin being spin eigenstates being superpositions of position eigenstates and vice versa. So it kind of carries around all these properties at once, but a lot of times we just ignore a lot of them that we're not paying attention to. Did that answer the question?
Yeah, so it means there are certain properties of a particle and they are independent of each other, and that forms the...
Yeah. So you can have you can do what's called like simultaneous eigenvalues.
How do you determine if it's a superposition or if it's independent?
So there's something called the commutation relation. And do you have markers in there? I didn't cover this at all, but it's a very big part of quantum mechanics. So you have, if I measure the energy of a particle and the position of the particle, and let's say it's in a position eigenstate, then this is, you have the eigenstate, you operate on it with the Hamiltonian first, the energy operator, then you operate on it with the position operator. So this is going to put it into an eigenstate of energy, and this is then going to select from the position eigenstates again and put it back into a position eigenstate. Now that may not be the same thing as doing the position measurement first and then the energy measurement. So the way that you often will see this written, so these two are not necessarily equal, and therefore sometimes you write this as this is a commutator bracket. It's just square brackets with a comma separating the two operators. So what this really means is that position eigenstates are superpositions of Hamiltonian eigenstates and vice versa. And another way to write this is xh minus hx is not equal to 0. If it's equal to 0, so like x and y are equal to 0, and also y and momentum in the y direction are not 0, but y and momentum in the z direction do commute because they don't interfere with one another. So this is called a commutation relation.
And they are not equal to 0 because of Schrödinger's equation.
So they're not equal to 0 because because the Hamiltonian eigenstates, energy eigenstates, are superpositions of the position eigenstates and vice versa. If they're not superpositions of one another, then the commutation relation is 0. So this is just another way of shifting the weirdness in different notation. It doesn't actually explain why some are.
But that operator comes out. The operator comes out from some. How do you get that H operator H operator?
So the H operator, remember, is the kinetic energy plus the potential energy. And so whatever system you have, you know how the kinetic energy is going to be written. And a lot of the time, it seems a little bit clunky, but a lot of the time what they do is they take, well, how would we write this in classical mechanics? Okay, well, let's just pretend that all the classical things are, all the classical functions, let's just turn those into operators and see if it works in quantum mechanics. And usually it does. So it's really weird. You have, there's a quantity called A, which is A mu in electromagnetism, which is the vector potential, the electromagnetic vector potential. And like you take a time derivative of this and you get the electric field, and you take the, what's called the curl of it, it's a type of space derivative, and you get the magnetic field or something like that. And they're like, well, we have this in classical mechanics, so let's see if we can quantize the electric field by turning this into an operator. And it works for some reason, but it's not really clear why it should work, it just does.
So operators are not derived from anywhere, they are just observed or they are in.
Yeah, they're kind of pulled whole cloth, and you see if it fits the, experimental results. But like, so, you know, if you have an atomic nucleus sitting, and you have an electron sitting in that potential, then you can write down Hamiltonian there, and you get h bar squared over 2m.